Hello and welcome to PCB Chat, where we talk with experts across the printed circuit design, manufacturing, and electronic supply chain fields. I'm Mike Buetow, president of PCEA. I've been covering the soldering industry for more than 30 years. During that time, I've seen lots of innovations come and go. I remember when an engineer from Hughes was using citric acid from oranges as a flux, and when Bell Labs introduced its first water-soluble flux. I recall when nitrogen was first used, and when no-clean pastes were rolled out and dismissed as lab toys. But I digress. Last July, Indium Corporation announced a partnership with SAFI-Tech, an Iowa-based startup that is creating no-heat and low-heat solder and metallic joining products. They call these supercooled molten metal products, and they have direct application to electronic soldering. We are joined today by Dr. Ian Tevis, SAFI-Tech's president and co-founder, and Dr. Andy Mackie of Indium Corporation to discuss this supercooling platform and what's next toward bringing it to market. Andy and Ian, welcome to PCB Chat.
Thank you, Mike.
Thanks, Mike.
The electronics industry has been chasing lower temperature solders for decades. That effort really sped up as SAC solders took hold in the wake of the European mandates to eliminate lead. But tin has a higher melting point than tin lead, so the transition away from tin lead eutectic, or 60-40, meant higher reflow temperatures, which in turn means more stress on the bareboard laminate, the typically plastic component packages, and so on, not to mention the higher processing costs due to the increase in energy consumption. Naturally, then, it would be a big deal if we could process solder with SAC 305 characteristics at a much lower temperature. Ian, let's start with you. What exactly is this new platform you've created?
Sure. I'm the CTO and president of SAFI-Tech, and we're bringing this supercooled liquid metal product to the market. And what it really is a new form factor for solder metal alloys. It's a core shell microcapsule. We call it a microcapsule. Others might call it a particle or a solder ball. It looks just like a regular solder ball, just a little bit smaller with a little bit extra on the shell. So like a core shell structure, meaning the solder on the inside is the metal alloys that you know and maybe love, SAC 305 and other metal alloys. And we put a proprietary shell on that. And then what that gives us and users of the solder material is access to the supercooled liquid state. That's just, instead of being a liquid above the melting point, you're a liquid below the melting point. That's just what's being called a supercooled liquid state. So we stabilize that, and so the users can access that and use a liquid version of SAC, a liquid version of bismuth tin, or other versions, different alloys at much lower temperatures than normal.
And so the IP is in the shell.
The IP goes towards the shell, which is like the magic that makes the technology happen. But there's also some unique application-specific IP, right? There's new ways of using it. We have a chemical-based process, like a solder paste would have a chemical-based flux to remove the shell, remove our oxide and organic shell. Also, there's an IP on what we call mechanical activation, or compression-based techniques, where we take a little squishy microcapsule and we squeeze out all the liquid metal, and it can flow out and form your solder joint that way.
So you've started with SAC 305. Is that the only solder that you've tried this with, or are you working on any other solder types?
So the technology is really a platform. And SAC 305 is like the biggest target, for a startup like us. But we've applied it successfully to other platforms. Bismuth tin being one of them. There's a lot of interest in that, or at least growing interest in lower temperature solder. Bismuth-based solders are easily accessible because of their lower melting point. We've also looked at some lead-based solders, because there's still a need. If you could process a lead tin solder joint at lower temperatures, there's a benefit there. But it's primarily been SAC, and it's primarily been bismuth tin.
What solder powder size or sizes have been tested to date?
Yeah, so the key to like the way the technology works is the solder spheres have to be small. We're talking 1 to 10 micrometers in diameter. We can go a little bit bigger. We don't really go smaller than that. And I'm not even sure if there are specifications. Maybe Andy can speak more towards it. If a Type 9 and Type 10 powder size have been truly defined about what sizes those are yet. But that's about the size we work on.
Type 9 or Type 10?
Talked about in song and legend. In fact, I was reading one of our competitors was talking about this, I think about 15 years ago when I first started at Indium. We're still sort of not seeing that powder size out in the market for standard system and package and those kinds of applications. However, having said that, the technology itself is something that we've been working on with SAFI-Tech for, I think, about 5 years now, 6 years. Ian, is that right? Yeah, so we've been sort of working together quietly in the background as sort of finding applications for this and so on and so forth. And we really got excited, I think, about 6 months ago when we realized that this was actually going to be usable potentially in some real life situations. It was no longer a laboratory curiosity. It was going into the kind of out into the real world. And it was at this point that I made the decision that I think it's time to sort of jump in and for us to work together to actively promote this out into the electronics assembly industry sort of broadly.
So at that size, though, you're really just pushing molecules around.
Oh, no. There's still a lot of room between us and molecules.
Fair enough. Where do you stand in the testing, and what types of machines have you used this on so far?
So we're early on in the testing. So we have done some basic level die shear type tests or component shear, and then some thermal shock. Right, for our SAC-305 prototype, we've sent them out for external testing for thermal shock. Minus 40 to 110, we're doing 30 minutes at each one of those for thermal shock, 1,000 cycles. So this is a BGA attach on an immersion silver FR4. So it's kind of our test vehicle. A BGA works well with our system. Immersion silver gives a nice surface finish for us to do our attach. So they're surviving the 1,000 cycles. There's a little bit of voiding that's occurring, but no full cracks. So that's kind of early level testing are promising for that. And we're working on the flux, right? The flux being used on a SAC-305 microcapsule now at 180 degrees Celsius versus 240. That flux will look pretty different and similar in some ways, but it has to be designed to work on our shell and at a lower temperature. So there's some development that needs to go on there, as well as print development. We're pretty good experts at making microcapsules and supercooling. Flux development, it's its own separate beast to tame.
So this is what I would call bearing the lead, right? Because we talked at the open about this being a low temperature or a lower temperature process. So what temperature are we actually talking about?
Oh yes, yeah. So for SAC-305, we're doing some processing at 180 degrees Celsius, as low as 165. It's still prototype. It's for select customers. We're doing some trials and demos for. But you're talking for, say, a bismuth tin, normally processed 165. I think some of them are getting closer to 150. We're at 135 degrees Celsius to process that.
135.
Mm-hmm.
So I think it's safe to say that the reflow profile looks significantly different than that for SAC-305.
Yeah, it's a ramp to peak. We try to go as quickly as possible to that peak reflow temperature. It's because that flux activity is always on. And when it's always on a liquid metal microcapsule, you can actually get joining at 20 degrees Celsius. It's limited, but you can get a little joining, and then that's it. Then you're done.
The testing that you've done to date, has that been from boards that were run through just convection reflow? And if so, was that nitrogen or just air environments? Or have you tried any other type of like vapor phase or anything like that?
So the the boards that we're talking about for this thermal shock, they were put through. We have a BGA rework station. We have kind of a wonky process to use it, mainly because supercooling of SAC 305 isn't down to below a usable ambient temperature. So we have this rework station. It's a couple extra steps to do it, where we're doing flux dipping and heating and such. But that system is originally done in air, and then Indium suggested, hey, do it in nitrogen, and here's the ppms that you should be looking at. And we did it in nitrogen to great effect. It does help quite a bit to do that, mainly because the lower temperature processing of the alloy, you do have less. You have more viscosity. You have less movement, the ability to wet and move, and so you want to limit that oxide formation as much as you can.
You did mention the test vehicle earlier, and you mentioned that there's BGAs on it. What else? What does the rest of that board look like? What other kinds of parts are on it? And was it designed really just to kind of look at the solderability of the platform, or were you also looking at what the potential dispensing and other characteristics might look like?
Yeah, the test vehicle was chosen to demonstrate all the parts, right? The printability of this material with a shell, make sure that the shell isn't disrupted. It's the use of a flux and to look at the solder joint, right? With these vehicles have SAC 305 solder balls on them, right? And they're a great test to show, because the SAC 305 ball, if it's not melting, it will collapse, right? And you can see that pretty clearly in the micrographs of the cross sections. And you're looking at IMC formation on our material, SAC 305, on the immersion silver FR4. If you have a thick intermetallic compound, 5 or more micrometers, well, you probably did that at a significantly higher temperature than 180, right? And so it was really to prove out, yes, like this, the basic science discussion of SAFI-Tech is over, right? This is a real solder joint. Here it is continuous SAC 305 IMC formation, survives thermal shock. Let's work together to finish this and bring it to market.
Andy, you mentioned a moment ago that you've been working with Ian for, I think, 6 years. When did SAFI-Tech first appear on your radar?
We've been working as Indium Corporation with SAFI-Tech for 6 years, but it was really, and I sort of heard about it in sort of song and story internally for several years, but it was only, I think it was about 6 months ago that we really started to pick up interest and make a decision that it appeared that there was something here. There was more signal than noise coming out of the data, and the potential applications for this also really started coming out. I think everyone's aware of the drive to use lower energy reflow for cost saving as one major thing, but also a major push within heterogeneous integration, for example, is the use of step soldering and the overall thermal budget for the assembly processes. So you have a high temperature assembly process, then a lower one, a very low one, and then ultimately, primarily caused by things like warpage and so on, you're going to want something that may want to be as low a temperature as possible. And so that's something that the SAFI-Tech technology really offers in a way that other materials absolutely do not have.
Has Indium performed any in-house testing or with its customers of this solder yet?
We've done our own internal testing and had some very positive results, which again is one of the reasons why we're starting to be interested in working with and partnering with SAFI-Tech and the team, precisely because we see the feasibility of this in the real world.
Are all the samples being made in Ames right now, or is anybody else taking on responsibility?
We still do make all the materials in Ames. It's all the solder microcapsules, any of the alloys. So we have equipment designed for each of the different temperature ranges to manufacture them. And our goal as a startup is to manufacture the material. And we draw a lot here in Ames, Iowa. We're on Iowa State's campus, so we draw a lot of the resources here from the tools available, but also the people here pretty well known for some of our metals tech.
Yeah, I'm going to touch on that in a moment. Here's a key question, right? How is this stored?
So a couple ways in which we store it. Kind of what's nice about the technology is that the shell and core of the microcapsule, they're different, and you can freeze the core and you can melt the core. As long as that shell is intact, you can store it as a solid if you'd like, and then you can get the liquid state back just by heat cycling. So like, for example, bismuth tin, we could freeze it in a minus 20 degrees Celsius freezer, and then we can remelt it at 139, 138 degrees Celsius and cool it back down to ambient, and 100% of those microcapsules are in the supercooled liquid state, which is pretty nice for transportation and long-term storage. Once it's in the liquid state, we store it under ambient conditions, like under nitrogen, under ambient temperatures, or we store it in a refrigerator setting, right? So we're trying to prevent the nucleation of the metal inside. And so you give it a little less energy to move around, it's a little bit harder for that metal inside to freeze. So we will sometimes store it in a refrigerator for up to 4 months in the liquid state.
When it's stored in a refrigerator, would it be at typical temperatures, or do you have to does it have to have really its own refrigerator?
Well, we store it at between like 0 and 4 degrees Celsius. I think that's one of the differentiators between us and a normal solder paste. We can't quite get the minus 20 storage temperatures for our products yet. That's one of the things that we're working on. We know the cold chain and its importance in the solder paste world. So right now it's stored as a separate, a separate system. The particles stored in one container, or the paste vehicle, whatever it may be, stored in another. Then they're simply mixed right when they're going to be used.
What's the process for mixing? I mean, with a typical jar of solder paste, you might just, stick a stick in there and swirl it around a little bit. So what are we looking at here?
Yeah, so I mentioned early on that we have a process for mechanically activating or kind of squeezing them. That could be true if you're mixing too. So the mixing process is important. So we typically will add small amounts at a time and then fold it in, trying to use the liquid to mix in the solder balls without applying too much shear. And once they're coated in a liquid, then they can be really sheared, because once those particles can slip over each other, that kind of water balloon-like structure, that elastic shell on the surface of this squishy particle, really prevents the metal from being sheared open during the process of mixing or printing.
Ian, I know SAFI-Tech is a startup, and according to your website, you're being funded by grants from the Department of Energy and Semiflex Tech, and at least one private equity group. Are there any other organizations or companies providing funding at this time?
No, those are the three main sources of us. A VC that specializes in kind of this deep tech, these new emerging technologies that come out that are trying to get over the valley of death, and there's not a lot of organizations that fund in this particular space. The government is one of them, and then the VCs, the kind of the next leg of that as they cross the valley of death. But we've been very fortunate that Semiflex Tech, this private public partnership, funded us for creating interconnects at PET, compatible temperatures for flexible hybrid electronics. So that's where that bismuth tin product I discussed came from. That was an 18-month project funded by SAFI-Tech and by this Semiflex Tech. But right now, we're working on a Department of Energy SBIR. Their high energy physics has a need to replace bump bonding for their wafer-to-wafer and chip-to-wafer attached. So they have these large format readout and sensor chips they use for high energy physics, like at CERN and other places. And it is difficult to assemble them because they're so large, and get all of the little IOs or sensor bits on the sides to connect, and you get deflection on the device edge from dynamic warpage, because these things are like 50 micrometers, 100 micrometers thick. So they have a lot of deflection that can occur. So we have a kind of a unique approach using microcapsules and self-assembly to put the microcapsules down and then solder them at a much lower temperature where the relative readout, the chip and the sensor are relatively planar to one another. So we limit the head and pillow, we limit the opens on the device edge.
Andy, in your long tenure in electronic materials, and I'm not calling you old.
I was wondering where you were going with that. Yeah. Seasoned veteran. Yeah,
veteran seems to be the catch-all, right?
Yeah.
Have you ever come across anything like this?
In my years, no, and it's fascinating. Going back to my sort of physical chemist days, many years ago, when dinosaurs ruled the earth. It's wonderful to see the nature of phase transition being absolutely turned on its head, because you know from the physics that you take an alloy, an ultra pure alloy, and I've seen this happen, for example, at IBM with their C4NP process. And you see a subcooled alloy. So you see these sort of little aliquots or little deposits of a subcooled tin silver alloy. And they're cooled below the solidus point, but they're still liquid. And then you can kind of watch them spontaneously solidify and do that magic kind of phase transition, but at a temperature that is well away from the what you normally expect from the standard, thermodynamic solidus temperature, and all of this is allowed by the kinetics of the phase transition, and to actually see this being implemented in solder itself is absolutely mind blowing. And I'd recommend, if anybody hasn't seen Ian and his team's video of taking what appears to be almost like a kind of a little solder grape, and then poking that with a micro probe and this sort of grape-like object under the microscope. Once its surface has been damaged and the solder leaks out a little bit, then immediately solidifies. And so it's actually the nature of the physical chemistry of the shell itself that Ian was alluding to that actually maintains that liquid phase, when your standard textbooks will be telling you, oh yeah, it's below the solidus, it's going to be solid, and it's absolutely fascinating. And so there's a fascination around the technology from a pure science point of view, but actually being able to turn that into something real and actually being able to make money out of the thing is really what also excites my business brain. So it's fascinating technology.
Let's talk about the applications. This is currently, getting funding from the U.S. government. However, I would think that military applications are probably way down the list insofar as what would be the immediate end product use.
Yeah, the requirements for mil-spec and others are quite high, for us to do. And we are, we're a startup and we have some limited testing capabilities, and we have Indium Corporation with a lot of more capabilities to do the testing. And you look forward towards those applications where they have, a need for a lower temperature solder, and the military has the excluded from the rules, and they can use lead tin, and that tin and lead are a great combination for solder, and they're a great combination for supercooling. So there are opportunities there, but right now we're looking for really a good entry level application where our uniqueness is unchallenged. Right? There's nothing else that can really do what we do, and the customers are in such a need that they're willing to do maybe a process change, try something a little different to make their products work.
I will add as well that we were just talking to one of our local universities yesterday about the increasing kind of overlap between some of the applications in medical, such as cardiac monitoring, and people on the battlefield. So that a need for the troops in action actually to have their vital signs be monitored at the same time. And so clearly the kinds of stresses, the kinds of 10,000 G type stresses that your hypersonic missile would need to withstand, that will necessitate a tin lead joint or something like this. Whereas some of these medical devices, and Ian already alluded to PET and maybe even lower melting types of substrate. And these medical type devices are really necessitating low temperature feasible substrates, flexible substrates, and so on. Of course, the corollary with that is that it can't go above 120 degrees C, 100 degrees C, 150 degrees C. So you really are limited. So taking a sort of a military aspect to this, there is clearly an overlap between the needs in the medical industry for flexibility, conformance to body shapes, and so on. And battlefield, and that all of these kinds of crossovers are occurring at the same time.
Just as long as it doesn't start reflowing at a temperature, I don't know, slightly below 35 C, right? If it was going to be embedded.
Right.
Yeah.
Andy, I understand from SAFI-Tech's perspective why it would want to partner with a major solder company. What's in it for Indium?
In it for Indium is the opportunity to be in at the ground level with an exciting new technology, which we believe it's probably never going to replace the whole of SAC 305 or any of the large scale solders. But again, with the emergence of these lower temperature requirements, step soldering, flex circuitry, and so on, and frankly, the wide-scale promulgation of these, particularly with an aging population, shall we say, necessity for that, we can see that now is a good time with the technology really starting to come into the limelight, real applications for this started to come forward. So we really wanted to be in at the basement level with SAFI-Tech, again, with whom we've been working for many years and very quietly under the radar. And so once the opportunity or the opportunities, as we're currently seeing, because we're talking regularly to customers and equipment partners and so on to develop not just the needs and the very specific needs and the materials for them, but also the processes that Ian's already talked about that go into this. So we have the whole wonderful thing of the material and the equipment partner and the process ready, and then we have the customer need. All kind of set up there in that wonderful triangle that makes things work. But we wanted to be ready so that once the scale up comes, we'd be ready to work with the team and be able to provide the ability to scale these materials as we have done with so many materials over the years.
So the anticipation then is that Indium would actually get into the manufacturing.
Absolutely, yes.
Ian, Iowa State has been ground zero for a few significant advancements in solder materials. Ames Laboratory, which is part of the Department of Energy and also a partner with ISU, developed and licensed one of the first silver copper tin solders to become mainstream in electronic soldering. So I have to ask, what's in the water there?
It's really more of the corn that we all enjoy and then breathe in as we drive everywhere in Iowa. I don't know. I think there's something special here. They've really built such a great environment here for metal technology. One of the inventors of that alloy you discussed, Dr. Ivor Anderson, is one of our advisors. Of course, he's a great guy with his beautiful mustache and his Hawaiian shirts. He loves. We like Ivor, and he really works closely with my partner, Professor Martin Thuel, since they're both there at the university and a little bit at Ames Lab. We know how important it is for these metallurgical advances to continue, and the technology that we invented really, Ivor was one of his PhD thesis was in supercooling of undercooling of metal alloys, right? When he was at UW-Madison. And so, this is a technology that, and you mentioned seeing some of that supercooling in some other applications as well. It's been there for a while, and it's just kind of coming together. How do we turn this into an actual material that can be used? And that was really the key thought that my professor as a postdoc he had here at Iowa State. to bring it to market. And I'm the one who just went into lab and made it work.
What's the next step? I mean, you have the ability to manufacture. You're proving out the platform. You have a major solder vendor as a partner. Andy referenced scaling a little bit ago, but how do you get there from here?
I think it's really deciding what is there. Where do we want to go, right? We have this platform, and it can be used in a lot of different ways in many different applications. And we're a startup. I have precious few resources to bring a product to market, and Indium Corporation is helping us with some of these customer interactions to ask the right questions, to kind of say, well, this is an interest to us, and because of X, Y, and Z. And so it's really like picking the target, and then customers have to touch it, and they have to try it, and then they have to lower their apprehension for it, and then get it spec'd into what they're building.
Now, listeners probably wouldn't know this, but Andy and I worked together years ago at IPC on various material standards.
Yes.
So, Andy, are the standards as they are written today open to accommodating this type of technology, or will there necessarily need to be some changes?
No, this is actually another reason why this is one of these kind of perfect storms of wonderfulness, or whatever the good phrase might be for it. It's the current version of the J Standard 20. I'm probably going to bore people to sleep right now, but there is a standard often referred to as J Standard 20. It's co-agreed with JEDEC. There's an IPC JEDEC agreement about this as being a joint standard. But it speaks to the temperatures that are of step soldering, shall we say, the temperatures to which solders in a hierarchy of solders in a single assembly are going to be subject to. So there's a high temperature, and there's a medium temperature, and there's a low temperature, and there's an ultra low temperature. And this is something that's actually falling out of the current version of the J Standard 20. I think this is going to be the F version of it. And the timing for this could not be better, because it's going back a little bit to those times of the tin lead solders and bismuth tin solders, and saying, hey, we've got to have a hierarchy of solder. So we've got to have a solder with a melting point somewhere around that of tin lead, which is around 183 degrees C, but it can contain lead. And what are the opportunities for this? So the specification from IPC J standards, the J Standard 20, next version is going to include kind of a 3-tier system. And so anybody who's looking at, well, how do we qualify a material into this process is going to have a kind of a lookup table of, so we need to do this with this specific package size, because it's dealing mostly with system and package type applications, heterogeneously integrated devices, and so on and so forth. So that's actually something that just this afternoon we're going to be talking to JEDEC about. So good call, Mike. Very good call.
I thought J Standard 20 was the component moisture sensitivity standard.
It is, but that is absolutely correct. But it is so much more than that, because it contains every customer that we talk to in system and package is talking about, well, okay, what's the allowable maximum reflow temperature that I'm allowed within this, based on this specification. And yes, it's moisture sensitivity, but it also, as an adjunct to that, is now becoming this kind of stratification of the allowable maximum reflow temperature that, again, speaks to step soldering, speaks to the needs of heterogeneously integrated devices.
Ian, I'm guessing that folks can find you on the internet.
Absolutely. www.safi-tech.com.
So the company is SAFI-Tech, and my guests today have been Andy Mackie of Indium and Ian Tevis of SAFI-Tech. For PCB Chat, this is Mike Buetow. Have a nice day.